can do that. All right, so everybody should be able to see my document camera. Give me a thumbs up if you can see my document camera.
Yes, ma'am.
All right, thank you. Okay, so let's look at a couple of things. If I'm given that we have a bird that's flying in a direction at, we'll fly at 10 meters per second. It's gonna be a pretty fast bird, maybe a peregrine falcon, and it's flying off in a distance of 35 degrees as I'm viewing it from the ground. So I'm looking up in the sky and I've picked my coordinate points and I've got that it's flying that direction from the ground. And we're gonna let it travel. We're gonna let it do that. So we have an initial velocity and we're given that it has an initial position. And let's say the initial position is going to be at, our position vector looks kind of like this. And this is, we're going to go in during this time, we're going to go that this is 6 meters at this direction, 45 degrees from our ground. So this is our position vector. This is our velocity vector. And we're going to be given an acceleration vector, okay? And our acceleration vector is going to be something a little weirder. And that's going to be at 0.5 meters per second squared. And this is a 20-degree angle. Now, when I have these three vectors, I can rewrite them in their vector coordinate system. So this is going to be 10 cosine 35 degrees in the I direction plus 10 sine 35 degrees in the J direction. Now, in each one of these cases, I've kept it as positive, but if my vector were going downward, I'd have to account for a positive or a negative depending on how I have it set up. My position vector is at 6 cosine 45 degrees I plus 6 sine 45 degrees J. And my acceleration vector is equal to 0.5 cosine 45 degrees, or 20 degrees, sorry. Just getting practice writing stuff down. 20 degrees in the I plus 0.5 sine 20 degrees in the J. So I've got a position, a velocity, and acceleration vector. We can go in and calculate numbers. So 10 cosine 35. I'm going to use a different color. So this is going to be 8.19 I. And this is going to be 5.74 J. This is going to be 4.24 I. That's 4.24 J. And then I've got 0.5 cosine of 20. This is 0.47. And this is 0.17 J. Now, if I want to look at an expression, okay, so I've got my my three individual vectors, and if I want to know the velocity at, say, 3 seconds, I'm going to use my velocity final is equal to my velocity initial plus my acceleration times time. Now that is a scalar quantity. So this is going to equal my 8.19I plus my 5.74J, because that's my initial velocity vector. And now I have my acceleration vector, 0.47I plus 0.17J. And if I have a scalar times a vector, all right, if I have a scalar times a vector, that's going to be AX in the I plus AY in the J. So if I put the T out here, this is just now going to be 8.19I plus 5.74J plus 0.47T, and that's in the I direction, plus 0.17J or T in the J direction. Now, I have to put the I's together and I have to put the J's together. So now I'm going to get 8.19 plus 0.47T, and that's all in the I direction. And I get 5.74 plus 0.17T in the J direction. Now I'm going to plug in for T, and we said 3 seconds. So I'm going to put in my 3 seconds here, and I'm going to put in my 3 seconds there. And I'm going to get 8.19 plus 0.47 times 3. This is going to give me a value of 9.6I. And this is going to be 6.25J. So basically, when you're looking at these vector problems, when we're dealing with 2 dimensions or 3 dimensions, you may want to use your vector notation. And these equations are going to work exactly the same, but I'm having to account for the various different directions. And so I'm going to use that same kind of information. We just normally take it apart and work through it. But I'm going to be putting in, these are all vector quantities. And normally when we've been working with the problems, we haven't been doing it in this vector notation. So hopefully that'll help you out with a couple of the homework problems that are out there, because really you're wanting to make sure you have the independent directions. So let's look at a different, yeah, there's a question.
I was wondering what the, I was kind of lost when you wrote down the, the A, then the capital A vector equals.
This right here?
Yeah, that.
This is the rule, okay? If that is a scalar quantity, I can apply it to both of the individual components. So if I were to go to my calculus book, I'd go to my algebra book, I'd go to a pre-calculus book. This is the math rule. That makes sense?
Yeah.
Okay, yeah, this is just coming out of the math rule. We're trying to reconnect the math back to what we've got out there. Other questions? Okay, hang on just a second. All right, so let's take a different projectile motion problem. Now, if I have an angle coming off of here, and we have a ball that's heading in this direction, and here's your factoid trivia question or trivia thing for today. All right, if I have a golfing iron, and I have TaylorMades and I have Callaways, there is no standard for what the angle is on a 3-iron or a 5-iron. Each brand has their own angle. So there isn't actually a standard. It's kind of odd because all your basketballs have standards, all of your footballs have standards depending on what league you're in. But if I'm playing with a 3-iron from a Callaway set of clubs is going to be different than a 3-iron from a TaylorMade set of clubs. But so that's just kind of an interesting factoid. So, but if I have a ball that's coming off, and we're going to actually say that this is going to come off at an angle of 37 degrees. And we're going to be given an initial velocity of, we'll make it 30 meters per second. We know that this ball is going to have some sort of trajectory that looks like this. Okay. And that trajectory could go, we could actually have it go and land someplace down here below the horizontal. We could have it land at some elevation up here. But it doesn't really matter. The function of this particular trajectory is not going to make any difference as to whether I'm landing up here, whether I'm coming down here. My questions that I'm asking may be different. So let's look at what we've got. So the first thing when I'm doing any of these things is I want to draw my picture. Because this is going to give you a good idea as to what is happening. If I don't have anything else and I have no idea how to start, the next thing I want to do is I want to get my X component and my Y component. So this is going to be 30 meters per second cosine of 37 degrees. This one is going to be 30 meters per second sine of 37 degrees. And if I actually go ahead and calculate that out, this is going to give me 23.96 meters per second. And this gives me 18.05 meters per second. And I can write my vector down as 23.96 meters per second in the I direction plus 18.05 meters per second in the J direction. All right, so let's take the situation where we're going to land this ball on top of the hill. Okay, and we know that the hill is going to have an elevation of say 6 meters. So it's going to be a pretty high hill. And I'm pulling numbers out of the hat, so this could be entertaining. We'll have to wait and see. We'll have to see what happens here. All right. So I want to know the time that it takes to get there. Well, a couple things that I know. I could be at 6 meters over here on this side, and I could be at 6 meters over here on this side. Now we have our independent equations. So let's write our Y direction equations. Okay, my change in Y is going to equal the initial velocity in the Y direction times time minus 1/2 gravity times squared. In the X direction, my change in X is going to equal my initial velocity in the X direction times time, but I have no acceleration, so that is going to be 0. I also have velocity final is equal to the velocity initial in the Y direction minus gravity times time. I also have velocity final in the y direction squared is equal to the velocity initial in the y direction squared minus 2 times gravity times my change in y, whatever that change in y is. Over here, I have no gravity, so this is just going to be velocity final in the x direction equals velocity initial in the x direction. Velocity final in the x direction squared is equal to velocity initial in the x direction squared. So I'm only going to end up with one set of equations over here. Well, right now I want to find the time for this one. So guess what? I'm going to use this equation. So we know the change in position is 6 meters. We know what our initial velocity is, which is 18.05 times time minus 1/2 9.81 times time squared. And if I do my 9.81 divided by 2, this is going to give me my 4.905 times squared. This is 18.05 times time, and that's minus, is equal to 6. I'm going to rewrite this so I have 4.905 times squared minus 18.05 time minus 6 is equal to 0. So now I'm going to solve for t, and I'm going to use the quadratic.
+6?
If I put this, yep, you're right. Hang on just a second.
Why would that be +6? Why wouldn't it be -6?
Because I'm at a height of 6, right? I've moved this over to this side. I've moved this over to this side. That's +6 is equal to 0. Because if I move it over to that side, that's negative. It's a -6. Because I'm just setting this up right here to give me my quadratic equation.
Okay, but could you do it the other way and have it be a -6?
Well, if I do it with a -6, I'm going to have a negative here and I'm going to have a negative there, and that's going to be positive, which is fine. That's up to you. I just like it work out because if I use my quadratic equation, this is going to be minus b plus or minus the square root of b squared minus 4ac divided by 2a. When I'm in, 0 is equal to ax squared plus bx plus c, right? And I just would rather use a positive. You can use a negative, it doesn't matter. So I'm going to solve for t. So I'm going to have a minus 18.05 plus or minus the square root of my minus 18.05 squared minus 4.9056 all divided by 9.81. Because 2a is 4.905 times 2, that's 9.81. So I have it right there.
So when you plug that into a calculator, would you make sure to use the positive first? Because of the plus or minus. But
well, here, I'll show you how I would, and I still do this today. I try not to do it all in one step. And I never have, and that's just me. So this is going to be 18.05 plus or minus. And now I'm going to, and part of it is it helps me tell if I've done something wrong along the way. So this is going to give me 325.8 minus . And this is one of the ways that why I like to do it this way, because now if I end up with this number being bigger than this number, I know I've screwed up. because I can't have a negative under the radical, right? So this gives me a chance to check, did I do something right or wrong? And I don't have to get all the way to the end and go, well, this, you know, get a syntax error on my calculator and not figure out where I made my mistake. So that's how I end up doing it. So this is going to give me, if I do that, I'm going to have my 325.8 minus 117.72. This is going to be the square root of 208.08. This gives me plus or minus 14.42, 1805. This is going to be 32.47 divided by 9.81, or 3.63 divided by 9.81. Gives me 3.31 seconds, or 0.37 seconds. So if I'm looking at my picture here, and this is why drawing your picture, both are valid solutions. It's going to be at 6 meters here, and it's going to be at 6 meters here. But if I'm wanting to find the distance downrange, so the other problem that I might want to have, right? So if I'm doing a problem that I'm going up here to the top of a hill, and I want to know my X direction, or the distance in the X, I'm going to need the time is equal to 3.31 seconds. If I use the 3.37, I'm going to get the distance that it went from here. I'm not going to get the distance that I'm dealing with downrange. So now if I do the distance, this is going to be the velocity, initial velocity in the X direction. And when we did that, times time, that's going to give me my 23.96 meters per second. And now I'm going to use my 3.31 seconds. This is going to give me 79.3 meters for downrange, because the seconds will cancel and I get that downrange.
May I ask where you got the 23.96 meters per second?
Right here, my initial velocity was 30 meters per second. At 37 seconds, my initial velocity in the X direction came right there. My initial velocity in the Y direction is that right there. And that's where, when we wrote down our velocity vector, we wrote this vector right there. So this is the initial velocity in the X direction. So I'm going to use the 23.96.
Okay, yeah, I forgot about that.
It's okay. Yeah, when we get these multi-step problems, sometimes we lose track of where we are. All right. So we might also have, what's the maximum height? We might want to know what the maximum height the ball makes. Well, at this point, if I'm drawing my vector at the maximum height, I have the velocity in the X direction, but what's in the Y direction? My velocity in the Y direction at the top is equal to 0. So if I want to find the maximum height that the ball has over here. In that case, I'm going to use, doing it a different color so we can kind of keep track. I'm going to use this equation. And that says that my velocity final in the y direction squared is equal to my velocity initial in the y direction squared minus 2 times gravity times the height max. Because we know that this is going to equal 0. So now I get the initial velocity in the y direction is equal to 2 times gravity times the height max. I'm going to take my initial velocity in the y direction squared divided by 2 gravity is going to give me my height max. This is going to be, now I go back to my y velocity, 18.05 meters per second. I'm going to square that. I'm going to divide by 2 times 9.81 meters per second squared. So I'm going to end up with meters squared over seconds squared divided by meters over seconds squared. Second squares cancel, one of the meters cancel, and I end up in meters, which is exactly what I want to be in. So if I do that, I'm going to take my 18.05, I'm going to square it, divided by 2 times 9.81, and I put in my parentheses. And this says the maximum height was 16.6 meters. Above the horizontal. And the ski jump problem is going to be the same thing. Okay. Now I look above here and I may be coming down the hill and I may have to take into a little bit of a different account for it. And you all have in your example videos, you have the ski jump problem. Is that making a little bit more sense?
Yes.
Okay, I'm going to stop sharing because I want to do a little bit of